Spring 1943. The docks of Britain's southern coast roared with the sound of machinery. Sparks flew, hammers rang out, and beneath the noise, a secret project was taking shape. A project so ambitious that even those working on it barely believed it could succeed. The goal: to lay hundreds of miles of pipe under the English Channel, carrying fuel from Britain directly to Allied forces after D-Day. The problem: no one had ever attempted anything remotely like it. At the heart of Operation PLUTO were two designs that would soon become legendary: HMS and Hamel. Both pipelines were marvels of wartime innovation, born from desperation and daring. The HMS pipeline, based on undersea telegraph cable designs, consisted of a lead core wrapped in steel armor and covered in protective jute. It could flex and bend, allowing it to be spooled onto giant drums for deployment at sea. Engineers quickly realized, however, that fuel exerted far greater pressure than a telegraph signal. To handle it, they developed high-tensile steel reinforcement and new welding techniques to seal every inch of pipe. The second model, the Hamel pipeline, was pure brute force, thick steel sections bolted together with precision-engineered flanges. While stronger, it was inflexible, requiring ships to carry and drop it piece by piece, a logistical nightmare in stormy seas. In a converted shipyard near Tilbury, naval engineers and oil specialists worked side by side, often through the night. Everything was improvised: the machinery, the measurements, even the methods. "We were making it up as we went along," one engineer later admitted. Failure just wasn't an option. Fuel stations were built along the English coast, disguised as ordinary seaside cottages. Inside, powerful pumps were installed, capable of pushing petrol through miles of pipe at immense pressure. One test blast sent a jet of fuel shooting over the pier, to the terrified laughter of the crew. To transport and lay the HMS pipeline, the Royal Navy commissioned an entirely new type of ship, the conundrum, short for continuous drum. These enormous floating reels, 30 feet high, looked like something from a Jules Verne novel. Each could carry up to 70 miles of coiled pipe, enough to stretch from Dover to Calais. When the first test lay began in the Solent, everyone held their breath. The conundrum slowly unwound its pipe across the water. 4 hours, engineers monitored pressure gauges and flow rate. Finally, fuel surged through, smooth, uninterrupted, perfect. Cheers erupted across the deck. It worked. But this was only the beginning. They had solved the engineering puzzle. Now they had to do it for real, across one of the most heavily monitored and dangerous waterways on Earth, without the enemy ever finding out. In a war filled with spies, submarines, and sabotage, secrecy was everything. Every order was coded. Every pipeline labeled as communication cable. Even Churchill himself referred to it in his notes with deliberate vagueness. Operation PLUTO had moved from theory to reality. The Allies had built a pipeline to invade a continent. Now they had to lay it under Hitler's nose. Late 1943. The wind off the Solent was sharp and cold. Men in oilskins hunched over test rigs while coils of new pipe steamed under the gray sky. What worked on paper often failed spectacularly at sea. Pluto's engineers learned faster than most. Every leak, every burst, every welded seam taught them something vital about the unforgiving language of the ocean. The first HMS prototypes were lowered from quaysides into sheltered bays. At low pressure the pipe looked promising, supple, spoolable, deceptively simple. But once pumps pushed petrol through at operational rates, weaknesses showed. Lead cores crept under strain. Joints, even expertly soldered, wept under pressure. In one early test a welded collar split and a geyser of fuel shot 40 feet into the air before the emergency valves slammed shut. Men scrambled. Someone swore. That failure became a lesson in metallurgy. Hamel trials were different, brute force against nature. The heavy steel sections had to be bolted and flanged perfectly. In the yard, crews wrestled with sections that weighed tons. In trials offshore, a Hamel joint that had passed inspection snapped under a sudden swell, A barge nearly capsized while men fought to keep the line from sinking into a rocky trench. Hamel bought strength at the cost of fragility in handling. Engineers adjusted. They changed alloys, thickened linings, redesigned flanges with redundant seals. They added sacrificial sheathing where abrasion ate into the outer armor. Instrumentation arrived. Pressure gauges, flow meters, temperature probes, instruments wired into nervous panels that the crew watched like priests watching omens. When a night test finally ran 6 hours without a leak, the men on deck dared to relax. A mechanic who had worked the pumps for weeks sat down and laughed until he cried. Alongside mechanical fixes, the human puzzle had to be solved. Laying pipe across a seabed meant navigation so exact that even a slight miscalculation could strand the line across a wreck or a minefield. Survey teams scoured charts and sent divers into freezing water to feel the seabed with gloved hands. They mapped channels, sandbanks, and cables. They learned where currents scoured the seafloor and where silt settled into pillows that would bury a pipe overnight. Conundrums, the massive coiling drums, were built and put to the test. The first full-scale spool proved temperamental. As it unrolled at sea, the HMS pipe kite and kinked in the ship's wake. A kink became a weak point, a future leak. Engineers modified payout speeds, redesigned guide rollers, and added swivel joint. Each iteration reduced the risk of a catastrophic kink from inevitable to manageable. Secrecy complicated testing. Trials had to be logged as communications cable tests in official manifests. Civilian dockworkers were given partial briefs and sworn to silence. Yet rumors leaked. A dockhand's wife would later recall the strange drums and the men who called them giant reels. The Germans, busy with their own war, took little notice, a quiet blessing. By spring 1944, the trials had matured into protocols. Crews could spool miles of HMS without a single burst. Hamel sections could be laid more safely when launched from calmer approaches. Pumps could push fuel at high pressure without overheating. Not every test succeeded. Some failed days before deployment, forcing crews to work overnight rewiring flanges by lantern light. But the failures had a purpose. Every rupture, every repair refined the system until it could survive the channel's mood swings. When general planners observed the test reports, they stopped calling Pluto a fantasy in meetings. The War Cabinet still spoke softly about risk, but the technical papers, stamped, signed, and smudged with grease, began to look like blueprints for victory. Engineers who had once been dismissed as dreamers were now essential. Their calculations, their welded seams, their cold water dives had turned an impossible idea into cold, hard engineering. And on one damp morning in May, after another all-night trial, someone wrote on a crate in black paint, "Pluto, ready by D-Day." The phrase was half taunt, half prayer, but for the first time it felt possible. As D-Day approached, the challenge shifted from testing to deployment. HMS drums and Hamel pipes were packed into barges, camouflaged as mundane supplies. Convoys moved under the cover of darkness, escorted by patrols and escorted through mined waters. Every spool, every flange, every valve carried not only fuel but the lives of soldiers who would depend on it across the beaches of Normandy. The channel was alive with hidden threats, sudden squalls, tides that could crush a pipe against rocks, and German reconnaissance planes circling offshore. Teams of engineers rowed alongside the barges, ready to dive at a moment's notice. Divers, clad in thick rubber suits, traced the path of the pipe along the seabed, anchoring sections against shifting sandbanks and dragging it over small wrecks. Visibility was often nil, and currents threatened to snap lines like thread. One misplaced anchor could jeopardize miles of pipeline, yet these men moved with precision, practiced in the language of danger and secrecy. Coordination with Allied command was critical. Radio silence was maintained. Every signal went through secure lines. Schedules were synchronized with landing operations, ensuring fuel would arrive exactly when and where needed. Crews used subtle visual cues, lantern flashes, colored flags, and prearranged hand signals, to communicate under strict blackout conditions. One slip, one misunderstood signal, and the whole operation could unravel. Even with careful planning, nature tested the engineers relentlessly. Storms churned the channel, whipping waves over partially submerged pipe. HMS coils threatened to unspool uncontrollably, and Hamel sections bobbed like rafts in rough waters. Crews worked through freezing nights, battling fatigue, saltwater burns, and the ever-present fear of discovery. Yet each successful joint, each mile laid, was a triumph of ingenuity and endurance. By early June 1944, the first sections of Pluto were successfully laid from the Isle of Wight to the French coast. Fuel flowed steadily into Normandy, supporting tanks, trucks, and aircraft in the first critical weeks of the invasion. Commanders who had doubted the feasibility of undersea pipelines now watched as their logistical nightmares were resolved by human skill, mechanical innovation, and courage under fire. Pluto's covert deployment was not just an engineering feat, it was a demonstration of Allied coordination, daring, and ingenuity. Every hidden spool of pipe was a silent victory, delivering lifeblood to the front lines and ensuring that the success of D-Day was not just about boots on the beach, but also about the unseen arteries that powered the invasion. Once the Pluto pipeline was operational, the Allies faced a new challenge: keeping it safe from German interference. Intelligence reports warned that German U-boats, reconnaissance aircraft, and frogmen could attempt to locate and destroy sections of the undersea supply line. Saboteurs posed a constant threat, and even natural hazards like shifting tides or sudden storms could sever connections. Allied engineers devised clever countermeasures. Sections of the HMS and Hamel pipes were armored or weighted to stay on the seabed, while some segments were buried under sand to avoid detection. Dummy pipelines and decoy installations were sometimes deployed to mislead German reconnaissance. Naval escorts patrolled critical stretches, and minefields were adjusted to protect the secret arteries without alerting the enemy to their existence. Teams remained on constant alert. Divers inspected the pipelines daily, repairing minor damage before it became critical. Special units conducted underwater reconnaissance at night, checking for leaks, corrosion, or signs of tampering. Communications were tightly controlled. Even routine maintenance was disguised as regular naval operations. Pluto's resilience was a testament to meticulous planning. Despite enemy attempts and the channel's treacherous conditions, the undersea pipeline delivered millions of gallons of fuel to the Normandy front. Commanders later credited these efforts with maintaining the momentum of the Allied advance, proving that victory often relied as much on ingenuity and vigilance below the surface as on the courage of soldiers on the beaches. The success of Pluto hinged on two distinct pipeline designs: the HHS and Hamel systems. The HHS, a flexible pipe wound on massive drums, could be laid quickly from tankers across long stretches of the English Channel. Engineers tested it in the Thames estuary before daring to deploy it in open water, ensuring it could withstand strong currents and the Channel's unpredictable weather. The Hamel system, by contrast, used steel pipes on floating pontoons, suitable for shorter, shallower routes closer to shore. This design allowed for rapid connection to port facilities in Normandy, ensuring fuel reached storage tanks and frontline units without interruption. Both systems required unprecedented coordination. Naval tugs, landing craft, and specialized winches worked in tandem, carefully unspooling thousands of feet of pipeline under the cover of darkness. Every segment of HMS and Hamel underwent rigorous quality control. Engineers monitored for microfractures, weld integrity, and pressure tolerance, aware that a single failure could jeopardize months of planning. Redundant pumps, valves, and junction points were installed to allow the system to continue functioning even if parts were damaged. The ingenuity of these pipelines wasn't just in their construction, it was in the way they transformed logistics. Pluto allowed the Allies to supply their armies at a scale previously unimaginable, enabling continuous armored advances and sustained air operations. By combining innovation, engineering precision, and daring deployment strategies, HMS and Hamel became symbols of wartime creativity that tipped the balance in the Allies' favor. On the night of August 27, 1944, the first sections of the Pluto pipeline were secretly deployed from specially modified tankers in southern England. Using covert convoys to avoid German reconnaissance, naval crews guided massive drums of HMS pipe into the channel, carefully controlling speed and tension to prevent kinks or break. Each drum unspooled hundreds of feet of flexible pipeline, slowly sinking to the seafloor. Meanwhile, at the Normandy beaches, engineers worked under blackout conditions to connect the pipeline to storage tanks and temporary fuel depots. Every joint and coupling was meticulously inspected. Any misalignment could lead to disastrous leak. Reconnaissance aircraft provided occasional overhead coverage to ensure that German patrols had no chance of discovering the operation, and radio silence was strictly enforced. The operation faced natural obstacles. Shifting tides, strong currents, and unpredictable storms threatened to break the pipeline or displace sections. Crews deployed anchors, weights, and tensioning devices to keep the pipe stable. Onshore, Hamel pipes were floated into position on pontoons, allowing immediate fuel transfer to tanks and vehicles. The success of this deployment was a combination of engineering mastery, precise timing, and daring bravery. By the first week of September 1944, Pluto was delivering thousands of gallons of fuel daily, directly supporting the rapid Allied push across France. The secrecy of the mission ensured that the Germans remained unaware of this logistical marvel until the campaign was well underway, highlighting the crucial role of innovation and stealth in modern warfare. Despite careful planning, Pluto's deployment faced relentless challenges. Sudden storms in the English Channel threatened to drag sections of the pipeline off course, while strong tidal currents caused unexpected stress on the flexible HMS pipe. Engineers constantly monitored tension and alignment from naval vessels, adjusting anchors and weights to maintain the pipeline's integrity. Onshore, the Normandy teams had to contend with mechanical failures in pumping stations, ruptured couplings, and leaks caused by minor imperfections in the pipe. Each incident required immediate repair, often under the cover of darkness to maintain secrecy. In addition, sabotage was a constant concern. German reconnaissance had the potential to discover and disrupt the operation, so camouflage nets, decoy equipment, and misinformation were used to protect critical sections. Communication between ships, engineers, and onshore units relied on secure, coded channels, ensuring coordination despite the hazard. Teams worked tirelessly, often through long nights, to keep the flow of fuel uninterrupted. By mid-September 1944, the combination of ingenuity, resilience, and improvisation allowed Pluto to achieve consistent delivery rates, fueling tanks, trucks, and aircraft crucial for the continued advance of Allied forces across France. This stage demonstrated that beyond brilliant engineering, the success of Pluto depended on human determination, resourcefulness, and the ability to solve complex problems under extreme pressure. Pluto's success left a lasting mark on military engineering and logistics. For the first time, a fully operational undersea pipeline had been used to sustain a major invasion force, proving that fuel supply lines could be extended across hostile waters without relying solely on vulnerable tanker convoys. The operation not only supported the rapid advance of Allied armies after D-Day, but also set a precedent for future military and civilian underwater pipeline projects. The engineering innovations, flexible HMS and Hamel pipes, portable pumping stations, and rapid deployment techniques, became study cases in military academies and civil engineering schools. Veterans of the operation later contributed to peacetime energy infrastructure projects, applying lessons learned under combat conditions to improve reliability and efficiency. Beyond technical achievements, Pluto symbolized Allied ingenuity and collaboration. Engineers, naval officers, and soldiers worked seamlessly across nations and disciplines, overcoming natural obstacles and enemy threat. Today, the story of Pluto stands as a testament to human creativity under pressure, demonstrating how logistics and engineering can decisively influence the outcome of war. June 1942. The Allied command sat in a smoke-filled briefing room in Whitehall, London. On the large operations map, a single red line crossed the English Channel, a fragile, hopeful line between Britain and Nazi-occupied France. But behind the strategy, one question loomed like a storm cloud. How do you fuel an invasion? Every tank, every truck, every aircraft that would storm Europe needed one thing above all: fuel. Without it, Operation Overlord would collapse before the first soldier set foot on the beaches of Normandy. Up to this point, fuel had been delivered in barrels, loaded onto ships, ferried across dangerous waters, then rolled onto beaches under fire. Each barrel weighed more than 400 pounds. Each one could be sunk, destroyed, or simply lost in chaos. The Allies knew that even 1 week of disrupted fuel supply could paralyze the invasion. By mid-1942, British logistics officers estimated that the advancing army in France would require over 1 million gallons of fuel per day. That meant thousands of tankers crossing the Channel, an easy target for the Luftwaffe and German U-boat. The math didn't work. The sea would become a graveyard of steel and oil long before the Allies reached Paris. At the same time, reports from intelligence units painted a grim picture. Nazi reconnaissance had already mapped many of the expected landing zones. Any major fuel convoy could expose the invasion's location before D-Day even began. In desperation, the British Petroleum Board proposed an audacious idea. If tankers couldn't safely bring fuel over the Channel, perhaps it could be sent under it. The concept sounded insane. A submarine pipeline stretching over 70 miles beneath one of the most turbulent bodies of water on Earth. It had never been attempted, not even in peacetime. The physics alone were daunting: water pressure, corrosion, flexibility, and the constant threat of enemy mines. But desperation often breeds innovation. Lord Louis Mountbatten, head of Combined Operations, listened in silence during a classified logistics meeting. Then, he simply said, "Gentlemen, we will need to fuel an army. Find a way." And with those words, the impossible became a military objective. Somewhere in Britain, a team of engineers, cable manufacturers, and oil experts began sketching what would soon be known as Operation PLUTO, Pipeline Under the Ocean. It would be one of the most daring engineering projects of the entire war, built not with guns, but with gears, cables, and courage. Autumn 1942. Deep inside the Ministry of Fuel and Power, behind layers of secrecy, a small team of British engineers gathered around a table scattered with blueprints and cable samples. The project had no official name yet, only a code: PLUTO, short for Pipeline Under the Ocean. At first, even seasoned engineers doubted the idea. Submarine cables existed, yes. Telegraph cables had crossed the Atlantic since the 19th century. But sending fuel, not electricity, through a pressurized, flexible pipe over the seabed was something else entirely. One crack, one leak, and the entire system would fail. The man chosen to turn this wild concept into reality was Sir William Fraser, an oil distribution expert from the Anglo-Iranian Oil Company. He quickly realized they would need a pipe both strong and flexible, one that could survive ocean currents and constant movement. Fraser brought in Hartley Rowe, a young naval engineer who had experience with undersea cables. Together, they reached out to the Siemens Brothers Cable Company and British Oil and Storage Limited. For months, they ran experiments in Portsmouth and the Isle of Wight, lowering test pipes into the cold waters of the Solent. Two designs emerged from the chaos. HNS, a lead core pipe wrapped in layers of steel tape and canvas, inspired by undersea telegraph cables. Hamel, a heavier, steel pipe version designed by engineers H.A. Hammock and B.J. Ellis, built for durability and higher pressure. Each had advantages. HHS was flexible but difficult to produce in large quantities. Hamel was stronger but much harder to lay across rough seabeds. To test them, engineers laid early prototypes between the Isle of Wight and the English mainland, a mere few miles, but enough to reveal endless problems. Water pressure crushed sections of the pipeline. Joints leaked. Oil pumps overloaded. Yet the failures only hardened their resolve. In a secret report to the War Cabinet, Fraser wrote, "The only way to ensure an uninterrupted supply line across the Channel is to construct a continuous pipeline. Success will depend on secrecy, precision, and speed." Churchill personally approved the plan in April 1943. The project's scope expanded overnight. Miles of steel and lead were requisitioned, factories converted, and civilian workers sworn to silence. The cable industry, once focused on civilian communications, became part of a covert military machine. Every worker knew only fragments of the plan, enough to do their job, but never enough to guess its purpose. Somewhere in a secure warehouse in Woolwich, a small brass plate was fixed to the first coil of pipe. It read, "Pluto, the pipeline under the ocean. Top secret." The countdown to one of the greatest engineering gambles in wartime history had begun.